Okay, so for this problem, we're going to look at a double slit interference pattern observed on a screen 1 meter behind two slits spaced 0.3 millimeters apart. 10 bright fringes span the distance of 1.7 meters. What's the wavelength of the light? So we know we need to use d sine theta is equal to m lambda. That's our equation for a double slit experiment. And we have a hint here, and it says first calculate the fringe spacing, the delta y, the distance between the adjacent bright fringes. And so that's important because we can see here it says 10 bright fringes span the distance of 1.7 centimeters. All right, so we think about our experiment. If we draw, our slits, right, and this is our screen. And so let's pick m equals 1. And this is our theta. This is our y, 1, because we're doing the first one. This is our L, so L is going to equal 1 meter. This is our D from here to here. And our D is equal to 0.3 millimeters. Okay, so the first thing is this 10 bright fringes span the distance of 1.7 centimeters. Well, that's not the separation for m equals 1. That's if I had a whole bunch of fringes. So if I had, like, imagine these are my fringes. And so let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, one more. So if those are my fringes, then the distance from here to here is equal to 1.7 centimeters. And I want to know this distance. Remember, they're all equally spaced. I want to know that distance, and that's the height y1 here. I could do it, pick any of them, but how do I do that? Well, if I have 10 bright fringes, then I have 9 spaces between, right? So this is 1 space, 2, 3, 4, 5, 6, 7, 8, 9. So what I need to do is I need to get y1, I need to say 1.7 centimeters divided by 9. And when I do that out, I get 0.19 centimeters. So that's what I'm going to use for my y1, 0.19 centimeters. Now I'm looking for the wavelength. So this is what I'm trying to find. And because I used m equals 1, this goes to 1. So really then lambda is equal to d sine theta. Well, I don't have theta yet. I know what d is. Let's see if we can figure that out. I know my second equation that from the lecture is tan theta is equal to y over L. So I'm using this triangle, and I'm going to say tan theta is opposite over adjacent, which is L, and so I can figure that out. So I know tan theta is equal to y is 0.19 centimeters over 1 meter, which is, then I can say tan theta is equal to tan inverse. And when I do this, this is actually 0.0019, right? Because I need to have them in the same units. So if I put it into meters, so I want the numerator and the denominator the units have to cancel. So I'm going to put 0.19 centimeters into meters in order to calculate it. And so then theta is equal to 0.109 degrees. And that's what I can use over here for this theta. And so lambda is going to equal d, which is 0.3 millimeters, times sine of 0.109 degrees. And the answer I get out is 570. And so remember, this is in millimeters. And usually the wavelength is given in nanometers. So millimeters are 10 to the minus 3, and nanometers are 10 to the minus 9. So I need to go 6 places to get from millimeters to nanometers. So 1, 2, 3, 4, 5, 6. So that's going to be lambda is equal to 570 nanometers. And that's my answer.